Okay, so now we know what a Markov model, Markov chain is, right? And the different components of Markov chains and what you expect for your quiz. If I give a question from Markov chains, it would be a problem statement, and you'll have to identify the different components, the three components of Markov chains yourself. You'll have to convert them to the graph yourself. And maybe you might be asked to compute probability of a certain sequence of events. The problem is that while this is very good and theoretically this is very fine, typically the problem is that it's not like just observable events that we're interested in. Usually there are a major assumption in Markov chain is that there's only one model which is generating the data. There's only one underlying set of probabilities which is being used to generate this data. And by that, I mean that there's only one coin which is being used to generate the head-tail sequence, or maybe there's just one dice which is being used to generate the sequence between 1 to 6, right? So that assumption is usually not true, because you may have multiple dices, you may have multiple coins, you may have multiple different underlying models that generate data. So for example, in this case, let this be the model for winters, for example. And it could be a different model for summers, and it could be a different model for spring, and a different model for autumn. And you can actually convert them across different days depending on the weather temperature or other things. In short, what I mean to say is that it's not necessarily just one model. Of course, in the Markov chains, it is exactly one model, and that is why we only use these probabilities. But once we talk about the hidden Markov model, there's another thing that we call the hidden states. And what we mean by hidden state is that we can simply not observe them directly. That is the only thing that is important here. So all the hidden states, we cannot observe them. The only thing that we can observe is that we can observe the value that is emitted from these hidden states. So for example, in the case of dice, we can observe the values between 1 to 6, right? So those are the observable states. But which dice out of the two possible dices was being used is basically the hidden state. Similarly, if we think about the text word, right? So here, for example, what part of speech is being emitted? We can observe the words are being emitted, we know that, but which part of speech was used to emit a particular word cannot be known, right? So that is the hidden state. Of course, if I tell you that there's some action word, for example, going or something like that, so for that you're going to say this is a verb, or this is an adjective, or this is a noun, and you can, just by looking at that, you might come up with the right thing. However, it's not something that is directly given to you or directly told to you. So in other words, a hidden Markov model will have observable events. For example, in the case of dice, we can observe 1 to 6 values, as well as hidden events. Hidden events are basically the events that are not observable, that we cannot see. For example, in the case of dice, if you have got a normal dice and a loaded dice, so that whether the data was generated from a loaded dice or from a fair dice, that thing is what we call a hidden event. And these are basically the causal factors in the probabilistic model. They are the ones that cause a particular value to come out, right? So that is the kind of introduction of hidden Markov models. And in that, I think we had an excellent example there. In the first case, we had two very good examples actually given over here. One of them was the coin toss model, in which you have got two different coins. So for example, here, another person is just flipping up coins, and he's doing a coin tossing experiment. And what he does is he only tells us the result of each coin flip and not which coin was used. So if there are two different coins with different, probabilities of heads and tails on both, that the coin being used is not known. However, the only thing that is known is that what is being observed from each coin. So for example, the net results, a typical observation sequence given here is head, head, tail, 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 head, tail, tail, head, and so on up till finally for t different observations, we get these t different values, right? And the idea here is that, as we discussed earlier on as well, we need to identify 5 different things from this. So the 5 different things, the 5 different, so and let's see here, each of them here is basically a possible Markov model, as we discussed, and each of them has different transition probabilities, different emission probabilities, and different number of states and different other options here. So each of them is a different Markov model altogether. When you have got only one coin with possible head and possible tail as a state, this is a one coin model, right? If you have got another, if you've got 2 coins, for example, and in 2 coins you can have first coin and second coin, and you can have some state transition probabilities and emission probabilities in each of these states, as is shown over here. So in state 1, you can emit head or tail, and the probability of each must be given to you. In this case, of course, since there are only 2 states, 2 possible emissions that can happen. If one of them is given to you, the next automatically is 1 minus the first one. So maybe one is given and the other need not be given. Similarly, for the second state, again, only one probability is required, the other can be calculated from it. And another thing is that since there are only 2 states, you can either stay in the same state or move out. And the probability of staying in the same state is alpha 1 for state 1 and alpha 2 for state 2. And the probability of moving out from each of these is 1 minus the corresponding alpha, right? So that is kind of very simple to do, but you need to identify these values. In the problem statement, I might only give just these values. So I must tell you that there are 2 coins, and on one coin, the probability of observing heads is 0.3, and on the other coin, the probability of observing head is 0.5, for example. And in that case, you need to infer on your own that the probability of tail is 0.5 in the second coin, and the probability of tail is 0.7 in the second coin. Similarly, if I just give you the values of alpha 1 and alpha 2, you should be able to identify that this is alpha 1 and this is alpha 2, and then automatically calculate the outgoing other 2 probabilities as well. So that is going to give you the transition probabilities. This one is basically the emission probabilities in each state. You need to calculate that and put them out graphically as well. So this is the observable sequence. Notice that this has nothing to do with coin 1 or coin 2 directly, because this is what we're observing. At the bottom, these are the states from which they were generated. And these states are normally hidden. We cannot know them. We have to infer them. And to infer them, we need to run some problems. In case of the third example here, which is a 3 coin model, each coin having different probabilities, each observing head or tail again is 1 or P1, 2 or P2, and P1, P2, P3 for coin 1, 2, and 3. And the probability of tail again is 1 minus P1 or 1 minus P2 or 1 minus P3 for the tail with the corresponding coin. So this is coin 3, this is coin 2, this is coin 1, and you can see the probabilities here. These are the transition probabilities. So transitioning from one state to another, these are the probabilities that will be used, right? And this is the observable sequence, and these are the underlying hidden states. Note how we are representing them here, and that is a traditional way of representing them. You need to use it throughout. And another example that they've taken up over here is basically the urn and ball example. And this is a very nice example because in this model, you've got n different models. And what I mean by model, each model is that in each model, there's a different probability of observing each color ball. So for example, if my urn 1 only contains red balls and no other ball, then the probability of observing a red ball in urn 1 is 1. And the probability for each of the other colors is going to be 0. And another urn may contain equal number of different color balls. So it's if there are 5 different colors, then the probability of observing each color in that particular urn is going to be 1 by 5, which is 0.2, and so on. So in each urn, you can actually see that the probability distribution of each observable color is different. What we observe, what is observable sequence, is basically the color of the balls. That is the only thing that is given to us. So green, green, blue, we don't know if this green came from urn 1 or from urn 2 or from urn n or whatever. So we have no idea where this green ball comes from. But what I do know is that the first ball that got picked was green. The second ball, after picking it up, we again put it back in the system, and again we picked another ball, maybe from the same urn, maybe from a different urn, and it was again green. Then there's a blue, and then there's red and yellow and red and so on. We can actually select different balls, and we can observe their colors. So this is the basic setting of your hidden Markov models. And just to tell you, maybe let's go back to this one. For a hidden Markov model, we have got 5 different important components. So there are 5 components for hidden Markov models and 3 components for Markov chains. Just like Markov chain, we have got the set of n states that you already know about. You already know about the transition probability matrix that starts from one state and goes to the next state, the probability of moving across states, in this case, moving across hidden states. Then you have got another observation sequence. So what was observed, we need to know that, right? The sequence of being observed. And finally, we need to have the observation likelihood or the probability, emission probabilities, as it is commonly called. And the emission probabilities is the probability of emission of each state, each observable state from a hidden state. So for example, in the case of a coin, let's say if you have got 2 coins and one is fair and one is biased, so we need to have a probability distribution of observing heads and tails in both the in basically, if I take this model, so this is a fair coin and this is a biased coin. So I need to have these probabilities. What is the probability of observing head in a state and a tail in the same state? Similarly, head and tail in the state. So for each state that is possible, we need to have the probabilities defined. And that is what we call the emission probabilities. So from this, I can say that these probabilities, these are the transition probabilities that transit from one state to another. And then the ones that are given at the bottom are the emission probabilities for each of these states. So for state 1, you can see that we have got 2 probabilities. For state 2, we have got the 2 probabilities of both heads and tails. Again, over here, we have got 2 probabilities for each state. However, the number of states are now 3, right? So that is the kind of thing that is required. These are the emission probabilities. Usually we represent them with the capital B. And in a particular state, they tell us what is the probability of observing a particular event. And finally, you need the initial probability state distribution. We usually represent it with the pi again. And this is the distribution that what is the probability we start in a particular state. So we need this again. Some states, of course, can be 0. However, and by that, if some state is 0, that means we cannot start with that state whatsoever. However, the sum of these pi's is always equal to 1. That is what you need to remember. Like we said earlier, in a first order Markov chain, each probability will depend only on the previous probability. So each qi will only depend on the previous qi minus 1. Instead of depending on the whole of the sequence, it will only depend on the single previous sequence. And secondly, if you want to compute the probability of an output observation, so in this case we have an observation with some underlying hidden states and observable sequences that is equal to exactly depend only on the single previous on the state only, right? So for example, if you want to say that head was observed on the 5th value, it will depend only on the hidden state from which it was observed and nothing else. Nothing else actually matters. So a very good example here is shown in the case of an ice cream. If again the weather can either be cold or hot, and depending on the weather, there's a certain probability of eating 1, 2, or 3 ice creams. So the alphabets that we observe is how many ice creams were eaten, whether a person ate 2 ice creams or 3 ice creams or 1 ice cream on a given day. And if it's cold, then in that case, typically you'll eat one ice cream by probability of 0.5, you'll eat two ice creams by probability of 0.4, and you'll eat three ice creams by probability of 0.1. And when the weather is hot, again, you're going to eat one ice cream with a probability of 0.2, two ice creams with a probability of 0.4, and three ice creams with a probability of 0.4 again. And notice that the transition probabilities are also given to you. So these are state transitions from cold to hot, or from hot to cold, or from hot to hot, or from cold to cold. And these probabilities are also given to you. Similarly, the pi probability, the probability of starting with a particular in a particular state, is also given. Starting with in a cold day is 0.2, and starting on a hot day is 0.8. So you can actually start with both; they'll have some value, and then you can continue on with what was eaten on the first day in a particular state, on the second day on a particular state, and so on. So I think again you can see that this is what it refers back to. It refers back to Rabiner, and from Rabiner they have actually identified the three main fundamental problems. The first problem is basically likelihood problem. And in the likelihood problem, we basically talk about an HMM, given an HMM with its transition probabilities and emission probabilities, as well as number of states and observable sequence, etc. Right? So that is what is given to you. So these are the five characteristics. All these five are known. The first question says that given the HMM and the observation sequence O, we want to determine the likelihood of what is the probability of observing this sequence given the model. So from this model, what is the probability that we can observe this sequence? The second problem that we're going to talk about is decoding problem, which is given an observation sequence O and as an HMM lambda. What is the best hidden state sequence Q from which these observable sequences were generated? So in this case, it's kind of like saying that you're given the O and you're given the lambda, and what you want to find is you want to find the hidden state sequence Q from it. And of course, this is very interesting because we'll always want to say that which state generated this data, and we can discuss that as we go along. And finally, you have got the third problem, which is a learning problem. Given an observation sequence O and a set of states in the HMM, you want to learn the parameters A and B. For this course, and like we discussed earlier, I'll only be working on likelihood and decoding. The learning problem is kind of, it's very interesting and very easy to do as well. However, due to lack of time, I think we'll skip it for this course. For learning, you typically use EM algorithm or expectation maximization algorithm. For problem one, we typically use the forward and forward backward algorithms. For problem two, we are actually going to use an algorithm that is called Viterbi algorithm. So that's the thing that we're going to work on along. I'll explain these three algorithms with a few examples that are already given here. And I think that is what is going to help you out. And if we now go to this part, again, it explains the 5 different elements of an HMM. It's very simply written. It's the same thing, the 5 things. And then you're given the 3 basic problems that can be solved using HMMs. In this case, you can observe that we have got the observable sequence O and a model pi. And of course, the model pi here, we can always divide it further into the 3 components: A, the transition probabilities, B, the emission probabilities, and pi basically for the initial state distribution, starting off with that. And the idea is, like I said, for the first part, the way you solve this problem is by using an algorithm that is a dynamic programming technique specifically, which is called the forward backward algorithm. We'll see the forward part of it. The backward works in a similar way, but forward is good enough for you, I think, at this point of time. The second problem that we're going to solve is to determine the underlying hidden state sequence that best or explains this data. So we can note that in this case, it's kind of evaluating the model here. So what is the probability of observing the data from this model? So this is a model evaluation technique. The second one is basically a decoding problem where we want to decode. The model is fixed now, but we want to decode it, decode the hidden states using the fixed model. And finally, in the third problem, we want to adjust the model parameters. Each of these values we want to adjust such that we can maximize the probability of observing the given data from the model, right? So that's the overall theme of this. We'll now take, I think, again a 5 minutes break, and I'll come back and we'll then discuss the both the problems and their corresponding solutions. And we'll see that with examples. So what we have studied so far is the different components of HMMs and what makes HMMs different from a typical Markov chain. And we have seen some critical examples, the three main problem areas where HMMs, where algorithms related to HMMs are applied. We'll only study the first two, of course. Like I've said, the third one we can leave it for now. But the main theme, I would say, of this lecture is that we are now aware of HMMs and their components. And this was the place where we left last lecture off. So from next lecture, we'll now start concentrating on the problem statements and the solution to solve these problems and what each problem statement means. And then I'll also explain what you need to do for quizzes. Typically, the quiz from this part, if I give a question to you on hidden Markov models, it can be of mainly it can be 3 different questions or 4 different questions. One question can be that I can actually give you a problem statement, something that gives you different numbers and different things. For example, here is a statement, the unknown ball model, this is the exact statement. We assume there are m distinct colors of the balls, there are 5 different colors of the balls. The physical process of obtaining observation is as follows. A genie is in the room and according to some random process, he or she chooses. And that some random process, I'll define the probabilities here, that he may choose earn 1 by the probability of 0.5 or earn 2 by a certain probability or earn 3. That's the initial state probability distribution. I'll give you that. That will be there in the problem statement. You'll have to find it out. I'll give you the transition probabilities. I'll give you the emission probabilities in each state. And you'll be asked to come up with a block diagram of it, something that is done over here. So a diagram like that. And from this, then you might be asked to infer probabilities or some other things. So that's the main theme here. And of course, this is just one model. I can give you 2 models, 3 models, and you might have to compare them along or something like that. So those are the kind of questions you should be expecting from this part. I might ask you to define the 5 different components or elements of an HMM. So you need to define all 5 of them graphically as well as in text. And you might, those are some of the questions that you might be asked from this. Another question I might ask you is that I'll give you the observation sequence and I'll give you the model parameters, I'll give you those. And then I'll ask you to compute P of O given lambda, or for example, P here, what is the underlying hidden state sequence. So those 2 questions are kind of very important, and I'll discuss how to compute these and see the examples as well in the next lecture, right? So let's take a 5 minutes break and let's come back in 5 minutes and let's see how to solve these 2 problems efficiently. Thank you very much.